Hello everyone, welcome back to my channel. Yesterday in the last video we talked about how we can design a circuit to display an hexa or decimal digit on a 7 segment display, right? We saw what is a 7 segment, how a 7 segment works, what type of 7 segments are there, and then we tried to write the tried to get the feel of how to write the code for this in Verilog, right? So in today's video we'll be seeing it how this code gets. We'll write the code on EDA playground and we'll see how the code gets executed, and we'll add some little bit design change in this, right? So let's talk about what design change we will be adding here. So if you can see here, we had made a table for with 8 bits for each of the connections A, B, C, D, E, F, G, and DP. DP was a connection to the little dot here, and we had tied this DP to 0 in our code, right? Now it might happen like someone wants to have a control on this DP. So here in this we don't have any provision for giving the user a control on this DP, whether he wants to turn it on or turn it off, right? So what we can do is we can add a pin here in the code, right? We can add a pin which is called okay, let me see how I can adjust it. We can add a pin as input DP, right? And we can remove this bracket from here. Now this input pin, we'll have to adjust this input pin in our code such that the DP is made controllable, right? So we'll shift this code a little bit down, see how we can shift it. I think we can right. So okay, so after adding input DP here, what we can do is here in the code, instead of writing temp as 8 tick B001, what we can do is we can break this code like this. Since we are now getting DP from the user, so we'll add DP here, and in this always @ digit, and whenever DP changes, right, we'll add a signal DP here. Since now DP can also change with digit, so whenever digit changes or DP changes, this code gets executed, but case will remain for digit only because DP is a user control input, right? So DP comma, and we can have that instead of the 8-bit code, we can remove this whole line from here, and we can just have the 7-bit code here, right? So 011111. So this is actually called concatenation. This is a concatenation operator, and what we are doing is we are concatenating this DP with the 7-bit string here. So when you combine this becomes an 8-bit input, right? So this is quite helpful in many applications. We will be looking further on this operator. So we can instead of this temp instead of 8-bit code, we can have DP comma 70B0001, right? Similarly we can do for all of these inputs here, right? And The final code will remain same because the common anode, common cathode logic will remain same here. This change will make our DP controllable, DP segment controllable. Okay, this was a simple change. So now since we have made this change, let's see how this code will be written in Verilog, right? So this code I've written, I've written this on EDA Playground. I'll paste the link of this EDA Playground project in the in the description. You can have a look at it. So I had written the code already, so I'll just explain. I'll go through this code here, and what I've written is here. I've declared the inputs and outputs as I had shown in the code also. So this is a 4-bit digit. Then we have the input for selecting between common anode code or common cathode code. Then we have the controllable DP here, and the output, where the 8-bit output which we need for controlling the 7 segment, right? Then we had discussed this in the previous video also, that we had taken a reg type variable here temp, so that since always block doesn't we can't drive any wire in always block, so we'll take a reg type variable here, and here just a little change, digit comma DP, right? So whenever digit or DP changes, this code gets executed. This is the case statement here. So for take D0, D1, D2, D3, for each of the digits we had separate codes, right? So that table I have written here. So 0, 1, 2, 3, and the order I have also mentioned here. The MSB corresponds to DP here, as it's clearly seen, and G, F, E, C, D, B, E, as it was shown in the previous video, the explanation which I gave here. The same thing I've written here also, right? So this is the block where you choose the code, and then for the common anode and common cathode, the assign statement, we will be assigning the temp value depending on the common anode or common cathode. For common anode, we will be negating the temp code, since this code was written according to the common cathode 7 segment, right? So we'll be just negating this, and if COCC is 0, then in that case directly temp will be assigned to it, right? Simple code. So the first thing now which I want to show is how the synthesized code will look like here. So in EDA Playground, you have tools and simulators available. So I have chosen Mentor Precision here, and in running synthesis in EDA Playground, you actually have to create a run.do file here, which I've created. You can find this template on Google also. It's very simple. So setup design. So here you will have to set which part you are using, which family or FPGA, which FPGA you are using, right? So here it is using Xilinx RTX 7, and the part number is there. Then we are taking our RTL as an input. We will compile it, synthesize it. Then this writes the code, and it reports the area timing, and it shows what is written inside this code, right? Output file list is also printed. So you have two options here. As you can see on my screen, there are two options: show netlist after run or download diff files after run. So whatever option which you want to choose, you can do it. I'll choose show netlist after run, right? Because that is more easy option. We'll get a pop-up. You will get a tab opened here, and it will show you the code, right? So after choosing all the options, we have to click on run here, right? We click on run. We will see the log generated here. Now see, it has started executing here, and after running it, we see that we get a code here, the synthesized code, which consists of some buffers here, output buffers and input buffers, and then usually they have used LUTs, and so this code is synthesized on using an FPGA, and this code, then what we'll do is this when we get this code, we can burn this on the Xilinx RTX 7, and then we can see how it can execute, right? So this is the code, but for now, since we don't have an FPGA, let's see what is another way to test this circuit, whether we are getting a correct output or not, right? It will not be a visual thing, but what we can do is we can send some vectors on the inputs and see what the output whether the output which we are expecting is there or not, right? So see here, I've written a test bench here, hex to 7 segment TB, and what the inputs which we have to drive, since they have to be driven from an initial or an always block, so they will be declared as reg here, so digit, COCC and DP, and the output which we want to see, like the output which we want to see, that will be driven, right? So that we can take that as a wire. Then first we instantiate the DOT here, hex to 7 segment, instantiated it, and we wire up all of the signals properly here, digit, COCC, DP, and then an initial block. We have taken an initial block, and what I've done is I've taken a loop here from 0 to 9, and what I'm doing is I'll display the I on this digit, like I'm sending this I on digit, so that in the circuit we get the digit as 0, 1, 2, 3, and and we are looking for is in the common anode and common cathode, right? What is the code which we are getting, and whether that code corresponds correctly to that digit or not, right? So here, as you can see, I have tied for now DP as 0, but we can have a look at how we can make DP as 0, 1, 1 also. So firstly, in common cathode mode, I'm displaying the digit and the 7 segment representation of it, and then I'm making COCC as 1. So now we need a common anode 1. So in that case also I'm displaying the same the code for the 7 segment here, and after displaying all of the codes, I clicked on $finish here, right? So for executing this, we need a simulator here. So we have a choice of simulators also. So let's choose Cadence 1, and we'll just run this code right here. And when it will run, you will see here we have got the displays. So for digit 0, the 7 segment representation is 0, 0, 1, 1, 1, 1, 1, 1, and since DP has been tied to 0, and if you see the 7 digits of this code, which they correspond to the same as we had discussed before also, 0, 1, 1, 1, 1, 1, 1, right? And for common anode type, since we are negating it, so it was 1, 0, 0, 0, 0, 0, 0, right? Similarly, if you see for 4, it is for 4 in common anode, if you ignore this DP bit, so it is 1, 1, 0, 0, 1, 1, 0, right? And if we see the same thing we had also coded before also. So our code is executing correctly. This confirms that the code is executing correctly and the output is coming according to the input and what we desire, right? So this project will be available on the in the video description. You can open this project and have a look at it and see how this code is written. Hope you have learned from these 2 videos a lot of things. That's all in this video for today. In the next video, we will be looking at how we can display a decimal number on 7 segment arrays, right? So here we have seen a digit to be displayed, but in a combination of digits, how we can display it on the 7 segment, we'll see in the next video. So please do subscribe to my channel for more such videos, and please like and share this video.